Hello, everybody. Today we are talking about overlapping sets. Let's begin with this lesson. In overlapping sets problems, we have people or things that are divided because there are groups with two characteristics that are intersected. And we're using double entry tables to solve. We prefer double entry tables to Venn diagrams, circles, or trees or equations because actually the double entry table is a better method, okay? The table looks like this one over here, all right? This table, it's a protocol 4 times 4 squares, and you are going to fill in 2 rows and 2 columns representing the presence or the absence of 2 characteristics, and they intersect each other. We have this box representing the count of elements that have both characteristics at the same time. We have this one and this one, which represent those element counts of elements that only have one characteristic at the same time, but not the other. And of course, there's also the possibility that we count some elements that don't have either characteristic. At the end of each row or column, we have the sum of all elements. And so these 2 quantities, the sum in the 2 rows or in the 2 columns, are mutually complementing each other so that the sum of the 2 columns or the 2 rows always gives you the total number of elements described in the problem. It's very important that for a faster filling up this table, you can use percents or fractions. Usually percents are superior because you can just fill in number 100 here, and in all the other boxes, the numbers represent percents, okay? So if you are asked for a quantity, you can work with percents until the end, and in the last step, you can calculate the quantity, okay? So let's take a look at the names of the columns and rows. Here, the names should represent the names of the characteristics that intersect. So you have to take a look at keywords in the problem to help you recognize when you use the tables, okay? So, and most likely, it's better if you use the same name of the characteristics, or at least a capital letter with the initial, right, letter of each keyword for saving time. Let's take a look at this example, okay? Imagine that you want to solve a problem where they talk about 2 characteristics that intersect, the gender and having or not having a car. Here, the most important word to look out for is the word of when you use percents or fractions, because it's always a percent of something or a fraction of something. That something is not always the total number of elements. It could be maybe a different quantity, a partial quantity, not a total. Example, if in this problem, or they talk about people of 2 genders having or not having cars, they could mention, for example, the men with cars could be referred to as this. 20% of the population are males with cars. Let's say that we are filling the total box with 100. So every square box here represents a percent. Okay, so if I want to fill in the intersection of males with cars. Here it says that it's 20% of the population. And 20% of 100, it's actually 20, right? So you would feel 20 here. But that's only because here the percent you're looking for, it's about the whole population, okay? What about if the problem had said 20% of the males have cars? So it's still men with cars. But now it's not like 20% of the total number of elements. It's 20% of the males. Say that the problem established that the men are totally like, I don't know, 30% of all people, okay, here. So if men were 30%, then 20% of the males would be 20% of 30, and that would be 6, okay? So the actual value for the males with cars would be 6% of the total number of people. Yeah, because it's the 20% of the males, which are 30 in turn. All right, so here, this 20% of 30% will equal 6%. What about if the problem hadn't referred to the 20% of the males, but instead to 20% of those who have cars are males? So suppose that the problem said that people with cars, you know, people with cars are just 40%. So that would mean 60% wouldn't own a car. But as they are telling you here that 20% of those who have cars are males, then it follows that those who have cars here, it's 40%. So 20% of 40% is actually 8%, right? So here, the correct value to fill in would be 8. So you can see that when you're filling the table with percents, you need to pay attention to this keyword off, right? Always pay attention to the keyword off. This is extremely important. Anyhow, you need to read, you know, slowly enough so that you can gather, you know, the correct information. Let's now talk about a different situation. Imagine that you have a problem where you're able to establish what the total of each characteristic is. So you will have the total of the rows, the total of the columns, and the great total. But here, there's no way you can find, just by knowing the totals, all of the intersection unless they give you at least one of them. If you are not given any intersection, then you cannot establish the real values, right, of the intersections, but only ranges of values. You can establish what's the minimum value, what's the maximum value for each of the intersections. Let's say in this problem, we want to find the intersection of x in the range for this intersection. So finding the max value and minimum value for those who have characteristic B but not A. Okay, how would we do this? Let's see here, people. It's very easy. First of all, what you need to do is to pick the values that correspond to the total of each column and row where your intersection is. Okay, so for example, x is part of row B and part of column not A. So we know that this count, X, cannot exceed any of the totals. So its max value should be 20. Okay? The max value of the intersection X should be 20. All right. So you can write here a little something. The max value of a box is simply the minimum of the column total and the row total. And that's it. Let's now talk about how to find the minimum value of X. Well, it's not always 0. Remember that the intersection counts, they always represent positive integer values or 0 in the worst case scenario, right? How can we find the minimum value of X? Well, it follows that since, for example, the sum of square box Y and X is fixed, it's 20, right? So it follows that this sum is a constant value. So if you wanna minimize the value of X, that means that Y should reach its maximum value possible. So in this case, what we need to do is find the max value of Y, and since that added with the minimum value of X should be 20, then it follows that the minimum value of X should be 20 minus the maximum value of Y. So take a look, people. What is the maximum value of Y here? If you just follow the directions in the previous slide, you just pick the least value of its two totals, that is 10. So all you need to know that is to perform this subtraction. 20 minus 10, and you get also 10. So the minimum value of X equals 10 as well. You can do that also using the box Z, because Z plus Y should be 40. You can maximize Z, find its value 30, max value for Z, and then subtract, right? 40 minus 30 equals also 10. All right. Let's now talk about a little something for the problem of 3 overlapping sets. So in this case, we now use the Venn diagram for 3 overlapping sets. When you have 3 overlapping sets, and you have several types of intersections, right? You have first those element counts that refer only to elements that belong in only one set, or elements that have just a single characteristic. Those would be only one. That's a key phrase you may find in a problem, right? Like m plus n plus p represents all the numbers or all the elements that only have one characteristic. Those elements who have only 2 characteristics are counted by adding x plus y plus z, which represent all the elements that have only 2 characteristics out of 3. Could be A or B, B or C, or A and C alone, okay? And T represents the intersection of all 3 sets. There's also the possibility that there are some elements that belong in no set. Okay, so we have this formula how you can count the total number of elements by adding the 3 sets separately, A plus B plus C, Then, in order not to count the overlapping parts, which are this and this, you can subtract ones, x plus y plus z. And since t is repeating 3 times because it's being counted within A, B, and C, so you can here subtract, take away 2 times t, and add the number of elements out of the 3 sets. So this would give you the total count of the elements. Okay,